はい。じゃあ、今日2回目のやつということで、やりましょう。Today is the number 2. We have 3 special seminar, and today is the second. Wait a moment, I will, レコーディング OK ね。ちょっと待ってね、シェア、ここじゃない。シェア、サウンドはまあ何もないや。はい。これだよな。なんか怪しいな、動きが。はい。じゃあ、シミュレーション for infiltration simulation で、today's number 2。ちょっと待ってね。Okay, last time we are learning about the formula of the theta psi, k psi. This is water content to pressure head or the permeability to the pressure head. ね、これ1回目のやつが体積含水率圧力水筒とかシータプサイか。で、K プサイということで、1回目6月14日、やりました。これクラスルームにも、この今、ズームで撮ってるのあるから、もし気になったらもう一回見てください。で、ダルシー則とリチャーズ式あんま説明してないんだけども、まあいいやと。で、今日は2回目。Says here that ここでね、ちょっと一番めんどくさい、陽解法と陰解法っていう風なやつ、ちょっと難しいんだよね。で、連立一次方程式を陰解法では解かならんっていう風な、ここまで、やってみます。I think this is the most complicated parts to understand the infiltration simulation or some kind of the numerical simulation. But here today, we would like to learn about the implicit. This is implicit が陰解法か。Explicit means 陽解法。These two methods. And at the implicit method, we have to solve the linear equation, matrix of the linear equation that is called system of the linear equation. So we will learn this. First of all, we'd like to review the previous time, last one. シータプサイバンゲネヒテンって読むのかな、この読み方、いまだによくわかんないんだけども、surely this is called バンゲネヒテン or some people say バンゲネホテン or some kind of this is a researcher's name, so it's better to ask to him バンゲネヒテン式 equation, シータプサイ this is for シータプサイバンゲネヒテン equation, but this is a terms of the last time topics. Yes, it's okay. Also, we learn about the なんだっけ Muirheim equation that combine the theta psi to the k psi, and these two parameters for the permeability and the water content is widely used. このバンゲネヒテン式とミュアレムの式を合わせたこの透水性のやつと保水性か。ここにもあったわ。これよく使われているので、ぜひ知っておいてください。And this is a kind of the very basic principle, basic formula for the Darcy's law. That is some law for the motion. Motion means the water movement. That is called Darcy's law. And we have to check the total water potential head, total water head. And the water will go, soil water will move from the higher total water head to lower total water head. this is the Darcy equation. The total head large H means the pressure head plus gravity head like this. まあ、これダルシー族、まあ、基本の式なんだけども、まだいいや。こんな形でこう、全水筒勾配で、勾配に比例してか、proportion to this gradient. で、that is a water movement amount flux of the water movement. これがまあ、ダルシー則で、運動則って言われてます。This Darcy's law is called the law of motion. So this governs the movement motion. This is the Darcy equation. Darcy's law. Yeah. まあ、ここもまだわかんなくてもいいです。It's okay if you do not understand here this equation now. But a little bit confused that yes, Darcy's law expression of motion. 運動の式って言われてて、ダルシー則と言われてます。だから運動をキネティックムーブメント、まあ、モーションのことを示すのがダルシー則。これね。で、もう一個、連続の式っていうのがあって、連続の式っていうのがこんな形。This is called continuity formula, and this governs some water continuity. So that means water is not generated automatically, or water is not vanished anywhere. So water amount or water budget is totally conserved. That is the continuity formula. まあ、連続の式ってことなので、なんかこう湧き出てきたりとか、どっかで消えちゃうとか、そんなことなくて、流れてった水はどっかにあるよ。continuity というふうなやつです。で、まあ、これとこれを合わせるとリチャーズ式になるっつうんだけども、まあ、そういうふうなことでちょっと覚えておいてください。And Richard's equation means that the combination of the Darcy's law, Darcy's equation, and the continuity formula, that is the Richard's equation. But surely this is a little bit confused that you can understand a little and a little. It's okay. まあ、ちょっとずつ分かればいいので、とりあえずこういった運動の式があって、連続の式があって、その合わせたのがリチャーズ式だよというようなことで OK です。待ってね。これ同じやつかな。これ同じじゃない。This is the same slide. This is older version that I made 10 years ago or somewhere, some days. So it's an old type. And 連続の式っていうのをちょっと、考えるといいかな。OK, this is the, これが連続の式ね。ちょっとここ丁寧に考えて、連続って何かなってことをちょっと考えて、continuity 連続。まあ、例えばこう縦にこうあって、まあ、ちょっと箱な。This is some kind of the soil column and divided into some parts. So this is some parts of the box. This is some soil column. ね、まあ、土のカラムがあって、こんな形か。土のカラムがあって、ちょっと待って。これか。これな。土のカラムが、こっち、いいかな。見えてるね。ちょっとズームの方でも大丈夫かなと。まあ、大丈夫だな。ここにこう、水が流れてるとしましょう。まあ、水が流れてるね。これが流れのフラックスで、この箱にね、So now we are focusing on this box, and this box is some part of the soil column, and Q1、Q2, and the water moved. Sometimes it is up, lower to upper or upper or lower. It's okay. So anyway, some there is some water movement here, and X is just the axis that we are now just focusing on. X で、Z って書いてある。Z、Z、Z、Z。Z ですね。Now we are focusing on the axis Z あ、書いてない。ちょっと待ってね。小さくなってるから、カメラをな。カメラどうしたらいいんだ？こうか。でっかくなった。まあ、皆さんはこれが見えてるけど、まあいいか。こんな形ね。で、ツイッターは、ウォーターコンテンツ。So, for example, this is、ボックスナンバーな。ボックスナンバーで、どうしようかな。これ1、2って書いてあったからな。まあいいか。C か。ABC にしようかな。A、B、C。まあ、いいか。なしいいか。どうしようかな。theta is water content. That means some kind of the water, total water volume on this box. Yes, theta. And okay. ちょっと待ってね。Now, time is t, and we would like to see the delta t forward of the time step. It's one time step forwarding at the t is the present time, and this is some kind of the future situation. Future means future on the delta t one time step, and then theta will be changed here to this one, so we can write. ちょっと色が一緒あれか。So now we are studying about the continuity, 連続ってことね。This water content is theta and theta t plus delta t, just one delta t time step for forwarding, and this means here, theta is changing with time. So sometimes theta will be reduced or increased because of the boundary water flux. So this is the changing of the theta. It's the left one, and the right one means the difference of the z. That means the change of the Q1 to Q2. Change of the Q. So, this is kind of the continuity and 連続。まあ、ちょっとまず日本語で言うけども、ある時間変化でここの場所のやつが増えた、あるいは減ったっていうのは、出たやつが多い、入ってくるよりも出たやつが多かったら減るよね。入ってきたやつの方が多かったら増えるよね。これが時間によるこいつの変化っていうのは、これの、差額で決まります。というのが連続の式。So, simply you can understand here that the water content at this box, this is some virtual box part, and this water content will be increased if the output is lower than increase when the output is lower than input. I mean that the input is high and the output is low, then water content will be increased. Water content will be increased with the difference of the input and output. Okay, theta will be decreased if the input Q1 is low and the output Q2 is high, then the theta will be decreased. So the change of the theta with time determined by the difference of the input and the output. This is the t-axis, and this is a kind of the t-axis, time forwarding here. So that is the continuity equation. It is called continuity. いいかこれが連続の式って意味で、水はどっかでこう湧いてきたりしませんよ。急に蒸発とかしませんよというふうなことね。So this formula equation showing that it's no water will be gushing up or sinking or evaporating and vanishing, but the budget is totally completed. Budget is equal throughout the time changing. And if so, of course, we can say that if there is some gushing or some part, something is leaking, some water is leaking, so we can add some parameters or some kind of sinking or gushing up with this. So changing of the water content is determined with the input and output and sinking or gushing up or something other parameter here. But now we do not consider some vanishing or evaporating or some gushing up or some seepage out from the outside. So the continuity equation is like this. All right. And we can see the minus here. So for example, what means the plus of this gradient? It's a kind of the depth gradient or gradient of the z-axis. And if plus means Q, this is just like delta z means the very small length of the z-axis. This is the z-axis. Delta z here. And this means we can write down like this, very small part, Q2 minus Q1. So if this means plus, that is the same as the Q2 is larger than Q1, then this is plus. Q2 is larger than Q1, then this equation becomes plus. But at that time, if the Q2 is larger than Q1, the theta will be decreased. So if this is the plus, this theta becomes minus. So we need this minus by symbol. ね、このやつは書き下すとこんな形になるので、Q2-Q1 がここの差額でどうですかっていう傾きな。これがプラスになるってことは、Q2 の方が大きい時だから、出てくやつが大きいので、θ は減りますよ。その分だけ減ります。というふうなことで、dθ、dt は時間の変化中減るよ。というようなことね。ここのちょっと連続の式っていうのが、ちょっとめんどくさいので、ここちょっとうまく理解してくださいなと いう感じです。I explained the continuity equation and we need minus here. Oh, this figure is very good that we are focusing on this box and Q2 is the output and Q1 is input. So if Q2 minus Q1 is positive, then this is positive. At that time, output is larger than input. So theta will be decrease. OK な。This is the continuity equation. 連続の式っていうのがそれです。で、今のは水の動きで、ソイルウォータームーブメントだったんだけど、ちょっとシンプルに、サーマルムーブメント、熱移動っていうのを考えると、ちょっと楽ちんなので、まずこれを考えます。で、サーマルムーブメント、熱移動っていうのは、もうほとんど水の動きと一緒。不飽和っていうやつがないだけで、あとは、飽和状態の動きと全く一緒なので、これを考えましょう。Let's think first of the thermal movement, some kind of the heat transferring. And this is very similar to the soil water movement, but the heat transfer has no unsaturated situation. Soil water movement has the saturated water movement and the unsaturated water movement, but at the thermal movement, there is no unsaturated situation, but it's very similar. So first of all, let's think about the thermal movement for example. Okay. Yes. So yes, this is some figure of the thermal movement, and you can see the fire here, and this is a hot place, and the thermal movement will be moving to the lateral, and we do not think some release of the heat now. It's a little bit, surely we have some release or some vanishing of the heat, but now we do not think this phenomena, this output. Okay, so heat is only moving with this path. こんな形で火があって、ファイアリングしてて、ちょっと放熱っていうのもあるんだけども、それ今考えないで、ちょっと方程式変わってきちゃうから、ここが温まって、めちゃ左右に熱が伝わるよ。こんな状態を考えましょう。これがね、今考えるやつね。で、ちょっと面倒なんだけども、さっきのここ、真ん中で熱温めてるぞ。で、この X アクシスが、X 軸がこっちにあるとしてな。で、熱の流れがあります。熱の流れも Q とか書くからね。で、ラージ T はテンパラチャーでそれぞれの温度ってなります。So now we are thinking about some vertical じゃない。ビジュアル、違うよ。何仮想的なってなんだっけ？そう、それ。バーチャル、さっきもバーチャルだってた。いいか。いいや。バーチャルボックス here, and the thermal movement is like small q, and large T is the temperature itself. And yes, this is some small, like wire or some cylinder, and that has the A cross-section area, and T is the temperature, Kelvin, and thermal flux is small q. ね、こんな形で断面積 A のところで、筒でも何でもいいんだけども、熱が伝わってて、X 軸があるとするよってことね。この図あるといいんだけどな。まあいいや。ちょっと次に書いちゃうけど、フーリエの法則だっけ、熱伝導のやつが、ほら、ダルシー則と似てて、熱のフラックス 熱の移動っていうのは、温度の勾配に比例するよ。ただし、大きい方から小さい方に流れるので、マイナスがつくよというふうな、これがダルシー則に似た熱の場合は、フーリエ則だっけというのがあります。This is a kind of the Fourier law that is some motion formula for the thermal. And, large T means the temperature. And this is the gradient of the temperature. And the thermal heat will be moving from the higher temperature to lower temperature. So we need minus because this gradient, temperature gradient means the lower to higher is the positive. So thermal will be moving from the high to low, so we need minus. And lambda is some kind of the proportion coefficient. So that is a Fourier law, law of motion, like Darcy's formula, Darcy's law. And we can write down like this. Yes, 1 plus 1 plus 2 means, yes, here. So we can calculate with the adjacent temperature difference and gradient with the delta x. So Q means, yes, you can remember. Can you remember here this one? And T1 plus 1, Ti plus 1. This is the number I. And this thermal movement is Qi plus 1/2. So this thermal movement is here. And the time is now, small t is time. It's a little bit difficult to confuse, but can you understand? There's no time symbol, but this is a situation of time small t, and Qi plus 1 second it can be calculated like this. And this is a little bit different from the solar movement, but this is just the same temperature T, large T, and small t is the time, and the temperature change means the thermal change. Time change, it's derived from the location change. That means input and the difference of the input and the output of the thermal make the difference of the time change of the large T. That means the temperature. ね。で、ここが出てくやつ、入ってくやつっていうのがあると、時間1個進んだやつのここの温度そのものが変わるよっていう風な数式です。これね、ローブモーションってやつと、コンティニュイティフォーミュラっていうことでこれと。で、ちょっと面倒だけど、Q の差額っていうのはこんなもん、お隣同士の差額の、X の違う分。これな、ちょっと面倒くさいね。お隣同士の出たり入ったりのやつの差額ってのは、出たり入ったりの差額は時間変化に、その分入っていくものが多いですか、出ていくものが多いですかで、ここの熱が上がりますか、下がりますかが決まります。で、その熱の動きっていうのはこっちのローブモーションで決まります。ね。Again, I'd like to explain this that this is some input and output of the thermal at some certain box like here, and input and output here, and the difference of the input and the output make the change of the large T. That means the temperature, and the small t is the time. Okay, this is the time differential. If the output is higher than input, then there is more, the temperature will be decreased. That is the continuity formula. And the thermal movement were written with this law of motion. This is the Fourier equation. As for the soil water movement, this is Darcy's law. Okay. これの2つが、で、もう決まると。で、そこら辺のお話なんだけど、ここにね、こう箱があるとしてね、1番、2番、3番って名前がついてて、タイム t、ラージ t、スモール t はめんどくさいけど、こう決まってたら、デルタ t タイムステップ過ぎたら、それぞれの1番、2番、3番のやつのが、t たすデルタ t のやつに決まると。で、こちらの方は、今現在の状況だから、測ればわかる。今の状況っていうのが、このラージ t の今の時刻のやつはこう、ノンって書いてあるけどね。タイム t。で、こっちの方は、デルタ t タイムステップ1個進めた、シミュレーションというか、キャルクレイティッドなバリューなわけで、こっちの t たすデルタ t はアンノンバリューということでね。This is the present situation that these values are known at the time step t, and we would like to calculate the situation of the t plus delta t. This is a little bit future situation. Then this is unknown data set here. Okay? で、これがこの式で、で、同じことだけども、これ同じじゃん。いいや。This is the same slide. Yes, this is just one. And so now I transformed the equation a little. Can you see this? Like this, but okay. So this is some of the continuity equation, and I transformed this with the, for example, left one is the t plus delta t equal is a transform, yes, like this. Just the simple transformation of this equation, and this is the same one, yes. Then now we can calculate with the present value. This is tt is present value and known value, and we can calculate to this one. And again, we can calculate this value with a little bit different neighborhood with the t, that's the present time, and then this calculate the t plus delta t, that's the one time step forwarding, time forward matching t plus delta t is calculate. This is explicit method, very simple, very easy to understand. Okay, so calculation gives t data set convert to the t plus delta t. Yes, very easy. This is the explicit method. これが妖怪法ってめっちゃ単純だけども、知ってる情報を組み上げて、この i 番目の情報を中心に、i 番目の気温の温度の t たすデルタ t 出しちゃったぜ。非常にシンプルなやつよね。です。で、これでもういいじゃんというふうなことになるんだけども、ここからちょっとが、妖怪法、シンプルでいいんだけども、やばいことがあるよと。注意しないといけないことがあるよということの例です。So, now, yeah, surely we can calculate the delta t time step forwarding. So, it's a very easy and simple, and this is called the explicit method to calculate the one forwarding time step, and very easy. But there is some important point for using the explicit method. And now imagine what happens if the fire is dismissed. Then this is some constant situation that this center is very hot, and the thermal will be moving to the lateral left and right lateral side, and the fire is stopping here. And this is some simple graph that the x-axis is the lateral vertical, no, horizontal one, and temperature, and the center is hot. And yes, we can easily understand that imagine that the thermal distribution will be decreased because there is no fire now, so will be cooler and cooler. This is very simple imagination. But for the explicit method, this is a very important point to be checked. And if we use the very longer delta t, then this, some Fourier equation can calculate the thermal movement with the present situation. And this is very hot and very high movement to the left and right with the Fourier Q equation. So time zero is the vanishing timing of the fire. Then this is like this. So thermal will be flowing to the left and right heavily. So then next delta t time step, this is be called rapidly. So first time step, this will be calculated like this, because this box and the neighboring with this box calculate much severe, much higher thermal transferring with the Fourier equation. Then the continuous equation shows that this point will be cooled rapidly. And this is the blue is the time step future. And second, we can see some peak here, just the adjacent of the center. Then next time, this will be calculated like this. ね、これが溶解法で注意しなきゃいけないことで、タイムステップ、デルタ t が肝というか大事で、長すぎるデルタ t を使うと、やばいことが起きる。というのが、すげえシンプルな。You know that the explicit method is very simple that we can calculate the delta t time step forward with the present situation very easily. But the delta t is the keyword of this calculation. If we use the much large, a little bit large delta t, then this calculate like this, such like some curious future condition or thermal distribution, right? So this is just the explicit method, and this is the Fourier moving motion equation and the continuity formula here. And so yes, let's back to this slide that we will imagine that when the fire is stopping, then the thermal distribution will be like this, and we never imagine that this point will be cooled rapidly, right? Like this graph. We never imagine this because we are assuming or expecting or simulating in our mind that this will be gradually changing. This is our assumption or hypothesis or some imagination that there is no sudden change, and change will be happen gradually. That is our imagination. And this imagination means we are assuming a little bit future with this condition. So then we can include this imagination into the formula like this. というわけでね、なんつうかな。へんてこりんな英語でずっと言ってて何言ってんじゃいってなるかもしれないけども、普通こういうふうにだんだん変わるなってイマジネーションしてるっていうのは、将来をちょっと考えながら、こう変わるよね、もともと思ってるというふうなことなので、それをこれに組み込めるのよ。で、ここで、インプリシットメソッドって言うんだけども、全部ここ、t の t の t で全部計算して t 足すデルタ t っていうのを出してたけども、将来もちょっと考えつつ、ここのフーリエのこの q は変わるんじゃねってことで、ここに今現在の情報だけども、t 足すデルタ t も含めてあげればいいんじゃないというのが、陰解法、インプリシットメソッド。で、これ、実は将来をちょっとイメージしながら将来を考える。So, here we can involve some imagination, future imagination in the equation by adding the situation here. For example, this is just a present situation, but we can add here the situation of the t plus delta t here or here. Yes, we have t value, present value here and here and here, and but we can combine the situation, not only present but also future. So that is the implicit method, and this is a little bit confused, but we can substitute the present situation t, large t, and the position is I, like this. So we use some value parameter f, for example, f, and if f is 0.5, then we use the present situation, substituting present situation to the future, half of future and half of present. If f is 0.5, then this is 0.5 and this is 0.5, means half future and half present. So that is some kind of the implicit method. So, for example, if f equals 0, that is called explicit method. f が0の時が陽解法で、0じゃなかったらもう全部陰解法です。0.01 でも 0.05 でも、もちろん 0.5 でも。で、1.0 っていうのが完全陰解法ってやつです。So, explicit method means f equals 0 only. But if f is 0.01 or 0.0001, then it is implicit, 陰解法. And if f is f equal 1, we call this full implicit method. So if f equal 1, then we use the only future data for the present situation. So full implicit method means these are all, every part is t plus delta t, t plus delta t, t plus delta t. So, but it is a little bit curious that we have to use the future data to calculate future. So it's a little bit confused, but like this. So we can convert the situation t as like this, and we can set or arrange the data again, and you know that these values are known data, so we can use these values here, but we now substitute these data to the これちょっとここに来た方がいいな。まあいいや。And the unknown value is here. So, so now we can show that for example, so by the explicit method, we calculate the station of the future station t plus delta t with the known values, and we can calculate this value with using the qi or q input and the q output or something that we can directly calculate here. But the implicit method, we need to calculate here by using this value, also this value too, and also this value, and this is not an unknown value, but this is known value t, that's t. But the implicit method using the future information too. So, これな。妖怪法だと、もう知ってるデータからこれ一発で計算できるけど、今度は知らないデータも使って、もちろん知ってるデータも使って、将来のデータを使って将来を計算する。なんじゃらほいってことになるけども、ここに注目すると、I 番目に注目すると、この数式化がこれ。But now let's focus on this number I box, and we have to calculate the t plus delta t, I box t plus delta t, but so with this number I box station, we can calculate like this. So if we can change the data through this, yes, this is a little bit confusing, but you can do by yourself that by focusing on this number I box, then the future I, this is the unknown, but also this is the unknown, then neighboring one adjacent box value. But focusing on this box, we can make one formula here. We cannot directly calculate the t plus delta t, this one. So explicit method, we can directly calculate this value, but now we can generate only one formula here by focusing on this box. And again, also we can focusing on this neighboring adjacent box. Then, voila, this is the last slide. Then we can make the linear equation matrix system of the linear equation like this. So we can focusing on the number I box Then large A, large B, large C are some kind of known data, but this is unknown data set. And this D is also known value. Okay, you can see the A, B, C, and the neighboring and the D is here. So we cannot directly calculate the T plus delta T, but by focusing on this ice box, we can make one line and adjacent one, adjacent one, adjacent one, and the boundary one, then yes, we can make the set of the system of the linear equation here. So then you know that this is a very simple matrix with the central valued and the only adjacent data. So this formula can be solved easily, a little bit easily. So we can say that the one-dimensional equation, numerical equation, is very easy because it's very easy to solve this system of linear equation, this matrix. We can calculate this very easily. So one-dimensional numerical simulation is easy. This is a one-dimensional equation, but if we have the three-dimensional, then there are another point, another value with another box, and not this. なんだっけこれなんつうんだっけ三角行列って言うんだっけThis is called the triangle 行列ってなんつうのリニア違うな、システムでいいのまあ、This is called triangle 行列。行列、日本語になっちゃったよ、もう。なんで、これ、解くの簡単なので、一次元のやつは簡単だと。ただ、二次元、三次元になると、もっと違うところにあちこちに数字が入ってきて、どことのやりとりで計算されますかというふうなことで、いろんなところに数字が出てきて、この計算が難しくなる。この連立一次方程式を解くのが難しくなる。すげえでっかい行列になるから、3万このボックスに分けたら、3万個の行列になっちゃうから、それであちこちに数字があると。ということで、インプリシットメソッドでも計算ができるよというやつで、エクスプリシットメソッドは、溶解法はデルタ t を調整するのが大変だし、めっちゃちっちゃいデルタ t にしないと計算ができないということがあるので、だったら時間間隔を長くしたいんだったら、このインプリシットメソッドの方がいいだろうと。So explicit method is very simple, but needed very, very small delta t. So, and we have to check if it's okay or not to applying the delta t. So sometimes, for example, there is some rainfall, then we need very, very small delta t. So if we would like to calculate more roughly or simply, large delta t, then implicit method is better. And this is very robust to calculate for the time matching. むしろ陰解法の方が計算は強いというか、発散しない、発散とか言ったらいいのかな。変な値にならない。なので、陰解法を使うんだけども、ある程度デルタ t も大きくできるんだけども、2次元、3次元になると、あちこちに数字があって、途端にこの行列が解きにくくなる。まあ、行列って言っても連立一次方程式なんだから、絶対時間をかければ解けるんだけども、大変だと。OK。で、so you can see the boundary, that means for number 1 or number n, that is the first or last. That means it is a kind of the boundary condition for example, thermal boundary condition or rainfall surface boundary condition, or some say, or the discharging condition, or some kind of the boundary condition make the first and last situation. ということで、今日はとりあえず、陽解法と陰解法、かつ陰解法ってのは、なんか不思議な将来のことを使って将来を計算するっていうことだけど、実はそっちの方が強い計算方法だぞ。で、しかもそれには、連立方程式を解くってことが必要になってくるけども、解けちゃいすれば、かなり強い計算の方、ロバストっていうか、ロバストっていうよく使うけど、発散しない、こう、変な値にならない計算方法だということです。So today we learn about the implicit and the explicit method. And the implicit method is very simple and easy to understand, but we need very small delta t. And the implicit method is a little bit curious that we have to use the future data to calculate the future. But this is resulted in to make some system of linear equations. So, this method is robust because the explicit method needed to check the delta t is okay or not each time. But the implicit method, by implicit method, we can use a little bit larger delta t and do not need to check the smaller delta is accurate and good, but this implicit method is very robust, strong to calculate the numerical simulation. And if we are thinking of the only one-dimensional movement, it's very easy to calculate this linear equation matrix, this matrix. But if we consider the two-dimensional, three-dimensional, the data is some scattering of the figure, and it's a very complicated and calculate. But next time, we will learn how to calculate this system of linear equation and how to build the programming coding with Fortran, for example. So that is next seminar, and the next is last. さあ、いかがでしょうか。陽解法、陰解法、ちょっと言葉に慣れてくれればまず OK なので、陰解法はこうだよって、陰解法には連立方程式を解くということが出てくるよのがあって、ただ連立方程式を解くっていうのはこのプログラミングで結構得意分野になって、その方法っていうのもあるよってことをまた来週だっけNext week we will learn about some coding method and the Fortran and how to calculate this system of linear equation rapidly. This is the next time topics. Okay, any question? OK ですか？まあ、だんだんね、慣れてくれれば。はい。First of all, let's familiar with the term implicit and explicit. So we can understand gradually, a little bit. So it's okay. So now, today we become familiar with the word of the term of the implicit and explicit. It's okay. It's just okay. はい。じゃあ、これで終わりにしたいと思います。ありがとうございました。めっちゃ暑い。暑いんだか寒いんだかクーラーが。はい、消す。